Hi, my name is Kevin, and I'm going to be talking about waves. And this is just basically an introduction to waves. I'm also going to be talking a little bit about the spectrum. And these waves are not going to be the ocean kind, like the subtitle says, but sometimes it's useful to draw analogies to the ocean kind of waves. All right, so let's get started with what is a wave, right? If we're going to be talking about waves, then we have to figure out first what exactly is a wave. Oh, also feel free to stop. If you have any questions about any of the content, feel free to stop me or like DM me on Zoom. So, all right. So firstly, what is a wave? So the formal physicsy definition for a wave is waves transport energy without the transport of matter. What does that mean, right? So normally whenever you think of waves, you're not going to be thinking about how they transfer energy or how the transfer of matter or whatever, but you're going to be thinking about this thing on the right. Here is going to be a squiggle, right? It goes up and down, right? So this is sort of like how you can draw out a wave, right? And in the end, these waves are going to be transferring energy. They're going to be moving energy from wherever they're coming from to wherever they're landing without like moving or without moving overall something from the left to the right, right? So first, I want to ask you guys, what are some types of waves that you can think of right now? Just like
Ocean waves.
what?
Sound waves, light waves, electromagnetic
Yeah.
waves.
Light waves, sound waves, electromagnetic waves. Yeah, those are all very good examples of waves.
Sun rays.
Sun rays. Yes, that is also light, right? So there are a lot of different types of waves. So you have like sound waves, light waves, heat energy, radiation, and so much more. So when I say light, I mean the electromagnetic spectrum, which we're going to be covering more in depth later in this class. Okay, so now we have a basic understanding of like how waves are going to be transporting energy for the transfer of matter and how they are can be represented by these like little squiggles. So when talking about waves, there are generally two different types of waves. So there are going to be transverse waves and there are going to be longitudinal waves. So transverse waves are generally what you think of when you think of a wave, right? They go up and they go down and they go up and they go down. So they go up, down, vroom would drop, right? So in these transverse waves, you're going to have these high points, and those high points are going to be called peaks, and you're going to have low points, and they're going to be called troughs. And you can kind of compare this to like an ocean wave, right? I said that ocean waves aren't like really waves. I mean, in some sense they are, but you can often use ocean waves to compare to real waves, and they're going to have, ocean waves are going to have peaks and they're going to have troughs. Just real waves are not going to be like curve, all of this curvy stuff, right? So transverse waves, they go up and down and up and down. So what about longitudinal waves? So longitudinal waves go back and forth and back and forth. So if you imagine on this wave, if you think of each of like everything on this line, you think of like, I don't know, points on all of these lines in a wave, in a transverse wave, all of those points are going to be moving up and down and up and down. And that's what's going to be creating this sort of wave pattern, right? So these points, they're going to be moving up, they're going to be moving down, right? That creates this sort of wave-like pattern, right? But instead of moving up and down, right, they're going to be moving side to side in longitudinal waves. So they go back and forth, right? So you can have like this particle, this little thing is going to go like to the right, it's going to go to the left, it's going to go back to the right, it's going to go back to the left. So in these longitudinal waves, instead of having peaks and troughs, we're going to have what's called compressions, where there are a lot of particles, right? So there's going to be a lot of stuff here. And we're going to have rarefactions, or places where there is less stuff, right? And this is seen most clearly in a spring. So whenever you have a compression, then that means that all of the springs parts are like really squished together, right? That's what a compression is. And whenever you have a rarefaction, it's whenever the spring is spread apart.
When will the longitudinal wave and transversal wave like kind of happen?
Right, okay, so I can explain that. So transverse waves can happen with, I mean, it just generally depends on like based on like what the wave is.
Light is a transverse wave, right?
Yeah, so like light
And
is
sound is a longitudinal wave.
Yeah, light is a transverse wave and sound is a longitudinal wave. Those are pretty much the textbook examples for longitudinal and transverse waves, right? So whenever you think of sound, sound is just a compression. Whenever you make a sound wave coming out of your mouth, you're going to have these places where we're going to have high pressure, or places with a lot of these little dots or particles, and places with less dots. And these are what we hear, right? However, with light, it generally goes up and down, up and down. So transverse waves may sometimes come from light, and then longitudinal waves sometimes come from sound, right? But there's obviously going to be more waves, right? Like I said before, like on the previous slide, we had a whole list of like all of the like a whole bunch of different types of waves. Drawing dots all over this, very cool. Right? A whole bunch of different types of waves. And generally you can sort these into either transverse or longitudinal waves. Okay, so now that we have these two classifications, generally whenever you see sound waves, right? Whenever you see a sound wave, you're not going to be seeing, like whenever you see a sound wave being represented, generally you see it represented like this up and down, even though I just told you that sound waves are longitudinal waves and they're generally drawn as these like compressions and rarefactions, compressions and rarefactions, right? So what's going on? Is sound longitudinal or is it transverse? Well, sound is longitudinal. However, whenever you draw it, you generally want to draw it as a like up and down wave because of these up and down waves are easier to because these up and down waves are easier to like think about. Okay, one of you guys pointed out that these drawings remind you guys of an old teacher, and that's because these drawings are from that old teacher, because I said before this was like taught earlier, so I'm borrowing half of his slides, but the later half is going to be different. So, okay. So generally we can represent these as compressions. We can represent these longitudinal waves instead of like drawing out all of these little dots, because it's a giant pain to draw a whole bunch of little dots and have a whole bunch of separated dots and draw a whole bunch of little dots. It's a lot easier to just draw this thing going up and down, right? Because this is just one line and this is just a whole bunch of dots, right? So generally, whenever we're drawing out these longitudinal waves into transverse waves, the more concentrated the dots are, so the higher density the dots there are, and also like pressure, I guess, then it's drawn as a high point. So that means that a compression would correspond to a peak, right? And a rarefaction would correspond to a trough, right? Because at a rarefaction, we said low density or low amounts of particles, there's going to be less, right? So generally these ups and downs represent the density of particles, right? So this means that we can draw these longitudinal waves, which are really hard to draw, into these nice little up and down waves, or transverse waves. So this is why you're going to see waves like sound that are supposed to be these compressional longitudinal waves drawn out as these up and down waves. All right. Did you have a question, or said somebody unmute and like proceed to remute? Okay, so I'm going to move on. So whenever we're talking about waves, the reason that these waves are so special is because they follow a regular pattern. And it's like, if you think about it, it's just a squiggle, right? You go up and you go down and you go up and then you go down, right? So you can break down these like long waves into little sections or one cycle, right? And these cycles will repeat themselves in the wave, right? So if you think about this, if we start at the green point, we go up to the purple point, we go down to the orange point, we go further down into the red point, and then we go back to the green point, right? But from this point on, this next section is just a copy of the previous section, right? We go back up to the purple point, right? So this purple point is similar to the purple point we had back here. This orange point in the middle is very similar to the orange point that we had on the left, right? And this red point is very similar to this red point on the left, right? This is because waves are going to regularly repeat, right? They're going to look the same if you shift it to the left or if you shift it to the right. So waves are composed of these repeats. So squiggle, repeats, repeat, repeat, so on and so forth. So that is like how waves are like repeating units, are composed of repeating units. So whenever we're talking about waves, we're going to be focused on some important values associated with these waves. So first of these important values is frequency, right? So whenever you think here like sound waves, right? You're going to say, oh, that sound wave is associated with some X amount of frequency, right? So frequency is like some sort of thing. Frequency can be represented by the wave, right? So essentially, frequency is the amount of like full cycles we get per second. So if you imagine we have like a wall on this side, right? And we start a stopwatch and the wave starts moving. And once that stopwatch hits 1 second, we stop and we look at how many of these squiggles, right? So how many of these ups and downs or cycles fully pass through, right? So if this wave going through this wall, if in 1 second, this entire section, so this up and down and this up and down were to go through the wall, right? You would say that there's a frequency of 2 because 2 full squiggles were able to make it through the wall in 1 second. So that is what frequency is. And units for frequency is going to be measured in hertz. So you're going to hear like, oh, that note is 440 hertz, right? So hertz just means 1 over a second. That's what these unit of frequency is. Okay. So another important quantity associated with waves is wavelength. So wavelength is essentially how long one squiggle is. Okay, so somebody asks about like having frequencies like 2.5 or like 3.2 or like even like a frequency of pi or something like that, right? So if we had a frequency that was like, if we had a wave, right, that instead of going through like this full 2 wavelengths, only went through like 1.5 of, oh, I'm saying wavelength, even though I haven't explained that, 1.5 squiggles, right? It's going 1.5 squiggles, right? Then its frequency doesn't have to be like a whole number, like 2 or 3 or 4. It can be like 1.5, or like if we move this to the right, it can be like 1.33333, or like pi if we like have it at exactly 3.14159, right? So these frequencies don't necessarily have to be like 1 or 2 or 3 or 4 or nice numbers like that. So next, another quantity associated with waves is wavelength. And wavelength is exactly what it says. It's the length of the wave, but it's not going to be like this full length, right? Because this is very, very long. It's not going to be that. What the wavelength is the length of one cycle. So it would be like the length from this dot to this dot, right? So this is one wavelength. So often whenever you're going to hear wavelength, you're going to hear that the wavelength is the distance from peak to peak, or the distance from trough to trough, right? So what's saying is that the wavelength is going to be the distance from this top, from one peak to the next peak, right? So one wavelength is going to be this section here, right? And if you think about it, one cycle or one squiggle is this is one cycle, right? Because this will regularly repeat here, right? So this also represents wavelength, right? So wavelength is going to be measured in meters because it's an actual distance that we can measure, right? And in general, whenever you increase wavelength, you have to decrease frequency, right? So if you decrease the amount, if you increase distance between this point, right? And if this wave is traveling at like a certain speed, right? That's not going to be changing. If this is longer, then you're going to get less of these cycles, right? Because these cycles are just longer, right? And it's going to take more time to get through the wall. So that means that frequency is inversely related to wavelength. So if you increase frequency, you have to decrease wavelength. If you decrease wavelength, you have to increase frequency. It's written nicely as an equation here at the bottom. Equations. So you don't have to like know this equation, but just like know that it exists. So frequency times wavelength is equivalent to the velocity of the wave. So how fast the wave is moving. Okay, so I'm going to move on to the next slide, which talks more about, I covered a lot of this on the previous slide, right? So wavelength is measured as distance between two peaks or two troughs, right? So peak to peak or trough to trough, and is also the length of one cycle, right? So in this image, the wavelength would be 1 meter, right? Because the distance from this purple dot to this purple dot is 1 meter, and it's going to be the length of one cycle. And frequency is how many times that a cycle occurs at a given time. So like we have this wall here. The frequency is how many full of ones of these cycles passes through that wall in a given amount of time in 1 second, right? So since it's a number of cycles divided by time, that's why it's going to be 1/seconds or hertz, right? I said earlier that the units for frequency is hertz. The reason is we have cycles divided by seconds or 1/seconds, and that's where the units for frequency come from. Okay, so next I'm going to talk about how energy is associated with waves, right? I said that waves, at the beginning I said that the definition of a wave is that it transfers energy without matter, without the transfer of matter or without moving something around, right? So the energy that a wave has is proportional to how tall it is or how high it is, right? So if you think about like an ocean wave, right? The ones that are less tall, they're gonna like run into the shore and they're gonna like, they're not gonna like change anything because they don't have as much energy. But the really tall waves, right? They have a lot of energy because they're really, really tall, right? And it's the same thing with energy in these types of waves, right? So how tall a wave is determines its amplitude, and it's like this sort of strength of the wave. So in the case of sound, if you have a high amplitude in sound waves, those sounds are going to be loud, right? So that's the loudness is a sort of the strength of the sound, right? And then for light waves, right? If you have a large amplitude, then that's going to represent that the light is going to be very bright, right? Because that's going to be the like strength of light, right? And vice versa, if you have a very like low amplitude or height, should probably explain. The amplitude is the distance from like this peak here to this sort of center line. And this is like sort of height of a wave, right? So how tall the wave is. That's going to be proportional to the energy. Right, and if we have that these tall waves have a lot of energy, then these sort of small waves or like less tall waves are they're going to be soft or they're going to be dim lights, right? So as it says, the purple is the amplitude because this is measuring from the center line to the very peak, right? Here, the center line to the very peak. So in waves, the amplitude or how tall a wave is proportional to its energy. So if the taller the wave, the more energy it has, the less tall the wave, the less energy it has. All right, so now I'm going to go over some review So, I mean, you guys listed so many waves, so I'm pretty sure you guys have a good lock on waves that you guys know. But let's look at this wave on the right here. So what is wavelength? Like just say if it's like the green thing, if it's the red thing, or if it's the brown thing or yellow thing, I guess. Where's my chat? Chat has disappeared on me. Oh no. Okay, so a whole bunch of people chatted green at me. And yeah, wavelength is going to be the green thing, right? Because I said that wavelength is a distance from peak to peak or from trough to trough, as this is the length of one cycle, right? So wavelength is going to be the green thing. Okay, how about frequency? Okay, some people are saying yellow, some people are saying red, but frequency is this yellow thing or brown thing. It's kind of like a little bit abstract because it's not really saying what it's counting. But frequency is going to be the number of times a wave like goes through a point, or how many cycles of a wave go through a point, right? So that means that we're going to have like a number for it, or I mean, there's going to be numbers for all of these, but so frequency is represented by the yellow or the green thing, right? I mean, not the green thing, the yellow or the brown thing, right? Okay, so how about amplitude? I mean, this may be a little bit easy because process of elimination, but whoa, a whole bunch of you said red. It's totally not because we already used green and already used yellow, but it's because you guys know what amplitude is. And amplitude is the height of a wave, right? It's the distance from the center line to the very peak, right? Okay, so that is a review of waves, wave frequency, wavelength, amplitude. So next, I'm going to be talking about the electromagnetic spectrum. Whoa. So electromagnetic spectrum is like, so what are EM waves? So EM wave stands for electromagnetic waves, and the formal physicsy definition for EM waves is the vibrations of an electric field and a magnetic field. And if you like draw out the EM wave, it's going to be like an electric field thing, wave-like thing, perpendicular to a magnetic field wave-like thing. Yeah, no, you guys don't have to understand that. But just think of EM waves as lights plus plus, right? So what you can see, but then what if we go like lower than what we can see, or what if we go higher than what we see? Those are what EM waves are. So EM waves are a stream of photons, right? And photons is like what we say as the like particle for light, right? So EM waves are streams of light, but then they go lower and then they go higher than light, right? And all EM waves, because they are composed of these photons, they're going to be all going at the same speed. They're all going to be going at the speed of light because all of these EM waves are just light, right? Because I said they're made of photons, right? And photons are just light, which means that all of these EM waves are all going to be traveling at the same speed. So with EM waves, there's going to be seven different types of EM waves, or 6 or 7. People generally you want to sit generally at 7. Oh, and down here is kind of like a review. Oh, sometimes peaks are called crests. I don't know. Okay. So down here you can sort of see the 7 different types of waves, electromagnetic waves. So I said on the first slide that EM waves transfer energy without matter, right? So if you think about like these waves, does it make sense for these waves? So if you think about microwaves, right? So microwaves actually use microwaves to heat up food. Whoa, the name actually means what it's describing. Wow. Oh. I think I've lost chat again. Oh, it's just hidden behind. Okay, nobody's chatting anything. Right, and also the sun, right? The sun is an example of how EM waves are going to be transferring energy without transferring matter, right? So the sun is going to be shooting out a whole bunch of waves, right? EM waves. And because of the sun, we get warmth on the earth and we get light on the earth, right? And we get heat energy and all that kind of stuff. So it makes sense that EM waves are going to be transferring this energy without like transferring stuff or matter, right? So if you think of also like with microwaves are going to be using microwaves to heat up food, right? Which means that those EM waves are going to be transferring heat energy without like moving anything, because in the microwave it's not like there's a whole bunch of like things that you can see that are flying towards your food that's heating it up, right? So microwaves are able to heat up food because they're able to transfer energy without moving matter or stuff, right? So with EM waves, the higher the frequency is, the more energy a wave has. And vice versa, the lower frequencies have lower energy, right? So on this spectrum, the left side is the higher energy side, the right side is the lower energy side, and because the left side has higher energies, they're going to have higher frequencies, right? And the right side, they're going to have lower energies, they're going to have lower frequencies, right? So gamma rays are going to be the ones with the most energy, radio waves are going to be the ones with the least energy and the longest wavelengths, and gamma rays are going to have the shortest wavelengths. Okay, so those are just the general overview of the types of waves and general overview of the types of waves and general information about waves that sort of applies to all of these waves. So now I'm going to go into each specific type, so radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma rays. So firstly, I'm going to be talking about radio waves. So
Do X-ray machines use X-ray?
Yeah, X-ray machines actually use X-rays. Things are actually named based on the types of waves that they produce. Well, did you also know that radios produce radio waves? Wow, things are actually named well. Can't believe it. Okay, so radio waves, they have the longest wavelength. So do you guys know what this tells about frequency? So I said in like an earlier slide that wavelength and frequency are inversely proportional, or they're going to be opposites of each other, right? So if we have the longer wavelengths, yeah, we're going to have the smallest frequency, right? Because big wavelengths means less frequency, right? Okay, so in radio waves can have wavelengths that range from 0.3 meters to 100 kilometers, and this is like a very wide range, right? They range from like, can definitely fit in your room to very quite far away, multiple football fields, many football fields, right? So these radio waves can be very, very massive to pretty large but reasonable, right? Okay, so radio waves, because they have the lowest frequency, right? I said that frequency is related to energy in EM waves. So radio waves are going to have the lowest energy. And the most useful form of radio waves, or what radio waves are mostly used for, is communication, right? So we have radios that can communicate over long distances. I mean, not very many people still use radios, but radio waves can transfer things like information through Wi-Fi or like through radio towers, right? So even if we aren't like actually using radios for radio waves, we have a whole bunch of other things that are like using radio waves. So the main sources for radio waves are going to be like our devices like TVs and smartphones and Wi-Fi and radio towers, right? So radio waves have the longest wavelength, lowest energy, and are used for communication, right? I guess their game lagging is related to waves, yes. And sometimes people use microwaves for Wi-Fi, which I'm going to be explaining a little bit later. But so the reason that radio waves are really good at communication is because they're very good at traveling long distances without getting messed up, right? So everything good from a radio wave boils down to it having a very, very long wavelength. Because it has a very, very long wavelength, it can easily go through the atmosphere. It can pass through like walls or most building materials, which means it can go through walls, which is pretty useful if you live in a house with a roof on it. Sorry, homeless people, but also the longer wavelengths also allow it to bend around corners, and it can bend around the materials that it cannot pass through. So this is due to a thing called diffraction and diffraction, which I'm going to be explaining in like a later class. But essentially, the longer wave is, the more it's going to diffract, and the more it diffracts, the more easily it can just bend around stuff, and the more easily it can just go straight through
Is that why you can? Is that why you can hear people around the corner?
Yeah, I mean, there's also a whole bunch of other reasons, like the waves are going to be like directly reflected off of the walls, but yeah, it's part of the reason why you can hear around corners, right? Because these waves are going to be diffracting, but you don't have to know that until later. So with radio waves, there's generally two different types. You can separate into like ground waves and actually no. There's two like special types of waves, so sky waves and ground waves. And the sky waves, these are the ones that have comparatively, they have higher frequencies in the radio like wave spectrum, right? And because of these higher frequencies, they're able to reflect off the ionosphere. So the ionosphere is like a layer of our atmosphere, right? So what this allows those waves to do is that if you like launch a sky wave like into the sky, then after it hits the ionosphere, it's going to start going back down, right? Which means that you can travel over long distances and over a whole bunch of things and go over all of the hills and mountains without having to deal with that stuff, right? So it allows you to travel a whole very, very long distances, right? But now people no longer use skywaves because skywaves can often be very, very inconsistent. So skywaves has gone disuse, and a lot of people like to use ground waves. So ground waves have the lowest frequencies in the radio spectrum, and if you think about it, since the radio spectrum is already the lowest frequencies, that means that the ground waves are going to be basically the lowest of the lowest in EM waves. And because of their really, really low frequency, they can just go over hills because, as I said before, their long wavelengths allow them to like go through materials that they normally can't pass through. So these ground waves can go over hills, and ground waves are actually used in submarines because ground waves can actually go deep underwater, right? So this is one of the use of radio waves. And the reason that radio waves are so good at traveling long distances is because of its long wavelength. So this long wavelength allows it to do all of these special sort of things. Note that radio is not good at traveling long distances, not because it's fast, because as I said before, all EM waves travel at the same speed. So radio is no faster than microwaves or light waves or gamma waves, right? So it's not because it's faster, but it's really good at going through things that other waves simply cannot do. Okay, now I'm going to be talking about microwaves, and it's going to be the second longest wavelength. Wow, it's almost like I'm going in order of the longest wavelengths to the shortest wavelength. So yeah, microwaves have the second longest wavelength, and they have a wavelength between 300 millimeters and 3 millimeters. So this is sort of getting more reasonable, right? I mean, this is getting kind of small, I guess, but still you can like still see it, right? 3 millimeters, that's pretty small, but not too small. And 300 millimeters, that's like pretty decent size. So whenever I said that, like sometimes people count it as 6 different types of EM waves, and that's because microwaves are sometimes merged with radio waves, and people just consider it just radio waves, but with shorter but with a shorter wavelength. Do you know that microwaves use microwaves? Whoa! So essentially, how microwaves work is that the microwaves. Okay, I should. This is the terminology as kind of like microwaves use microwaves, so microwaves are okay. I'm going to say microwave ovens. Microwave ovens use microwaves. So the microwaves in the coming from the microwave ovens, they're going to be going through like everything else except the water and the fat. And essentially what the microwaves do is they cause the water and fat to start moving, and movement generates heat, right? If you like run around, then you know that movement generates heat because you start becoming really warm after you're like running for a while. So it causes the water and fat to move, and this moving causes heat, right? So this is how microwaves are going to be heating food. They're going to be going to directly to this water and fat, and they're going to be increasing them. Whoa. And then microwaves can also move through a whole bunch of things because it has like some level of wavelength, but it's not going to be as good as a radio wave. So they can move through clouds and smoke and weather. And as such, they are used. So some sources of microwaves are radar. So radars generally use microwaves because it's microwaves will reflect off things that you want to see, right? Because radio waves are going to like go through everything, right? But microwaves are going to like go through a lot of things, but not go through others. And we're interested in what they're not going through, because then we can figure out what they're not going through is, right? So radars will use microwaves. Also, another source of microwaves is, big fancy words, cosmic microwave background radiation. So essentially what it is the radiation left from the Big Bang, and yeah, those are microwaves. Okay, so next I'm going to be talking about the infrared. So the infrared is going to be longer than visible, and in particular has a longer wavelength than visible lights, and particularly red, even though I haven't explained visible light yet. But visible light is coming next. They have longer than visible. They're going to be longer wavelengths than visible, smaller wavelengths than microwaves. And they're generally going to have wavelengths between 780 nanometers and 3 millimeters. So a nanometer is 10 to the -9th in scientific notation. So it's like you can fit 1 million nanometers into 1 millimeter. So obviously 780 nanometers, that's going to be very, very, very small, right? So we're ranging from pretty small to very, very, very small, right? And that's where infrared. And we're not even halfway there yet, because this is still number 3, and we've got 7 to go through, and they're already really small. But infrared waves are also called thermal radiation. That's because heat is generally associated with IR. So if you have some like heaters use IR waves to heat up the room, right? If you have a little space heater at your house, then some of them will be using IR waves to heat up the room. So generally the major sources of infrared is things that produce heat. So the sun, that produces heat, and that's going to be shooting off infrared. So you have a nice picture of the sun here. And also fires, that produces heat, so that's going to be a source of infrared. So infrared waves can sometimes have negative effects if you're like exposed to it. So it can cause eye damage and damage lenses. So basically the infrared like goes to your eyes and it messes up a little bit of the lens, and that can kind of harm your sight. It can also cause skin damage and color change on your skin, but does not cause skin cancer. So skin cancer, although the sun does cause skin cancer, it's not going to be from the IR coming from the infrared waves coming from the sun. It's going to be coming from the ultraviolet, which is going to be explained a little bit later. And infrared mainly causes heat. So infrared is most useful for thermal imaging. So you see this picture of a doggo on the right here, and it's being thermal imaged, right? So we have the eyes. A lot of the heat is going to be coming from the eyes and the mouth. And this is also how night goggles work. So night goggles are going to be looking in for the, while we won't be able to see very much visible light, we can see the infrared, and it's like seeing the heat, right? And it's also useful for astronomy because infrared can pass through stuff that visible cannot. So seeing stuff through stars and seeing stars through the dust. Okay, now we can get to what we're used to. So visible light. So visible light is just basically what we can see. And it generally ranges from 380 to 750, as you can see on the right. And each of these can be divided up into what we perceive as colors. So violet, blue, green, yellow, orange, and red. If you think about it, we go from 380 to 750, and we think about it, this is actually a very small portion of the electromagnetic spectrum, right? So previously we had like infrared. Whoa, it's going from 780 nanometers. So that's like 10 to the negative 6 to 10 to the negative third. Wow, that's like 3 digits difference. 300 to 3, that's like 2 digits difference, right? And then in the visible light spectrum, there's just like no difference in digits. It goes from 380 nanometers to 750 nanometers. So this is a comparatively small portion of the EM spectrum, but it accounts for everything that we can see. So visible light is between infrared radiation and ultraviolet radiation. And obviously the most obvious source of visible light is the sun. Wow, the sun produces light so that we can see. And also artificial lighting. Wow, if we can use it to see things, then it must be visible light. Cool. Also, if you notice on this side, purple is not included because purple is actually a hoax. I'm going to be explaining colors later, like a different week, but there is no specific wavelength for purple because purple doesn't actually exist. So what we see as purple is what happens when we like see both blue and red light combined together, and that's what we see as purple. So purple doesn't actually have a frequency associated with it. That's what I mean when I say purple is not real. I mean, you're definitely going to be able to perceive purple, but there's not going to be a frequency with it. So next, I'm going to cover ultraviolet. So ultraviolet is generally has wavelengths between 380 nanometers to 10 nanometers. So this is getting pretty short. I said that 1 nanometer was.
I've heard of that ultraviolet light can determine blood if it's been wiped out or something.
Did not exactly hear what you were saying there. But.
So I've heard that if you use ultraviolet light and put it on something that used to have blood on it, it can show you a bit like those hands.
Huh, I did not know that.
That's like
Yeah, so-
forensics, right?
Forensics, yeah.
Oh, sorry. Yeah, sorry, forensics. I've always read it as forensics.
guess I missed some of. Well,
Yeah, go ahead.
I guess I missed some of these uses down here, but I guess ultraviolet can also be used for forensics, but generally ultraviolet is going to be shorter wavelengths than purple, and there's going to be lots of sources for this, like the sun. The sun produces ultraviolet light, and it's going to be what causes skin cancer if you're under the sun too much. And black lights, those are a source of ultraviolet light. And you have a whole bunch of artificial sources like these black lights, and also lasers can produce ultraviolet light. So the primary use for ultraviolet light is generally to kill bacteria. So if you've seen like a water facility plant, they're going to have like these giant vats of water, and they're going to have like this light or these bulbs coming down, this faint purple glow coming down from the top. And that faint purple glow is ultraviolet light, and that the ultraviolet light is disinfecting the water. That's what it is doing. Also, ultraviolet light is useful for tanning, and ultraviolet light is what causes tan. Also, there's a thing called fluorescence where some plant life absorbs ultraviolet light, and then it releases that as visible light, and it causes glows. And also another use, like that's not included here, I guess it's for forensics and for blood. I'm not entirely sure how it works, but Yes, ultraviolet light can be used for forensics. Whoa. So there are also many dangers to ultraviolet light. So ultraviolet light can cause sunburns, right? If you've been in the sun for too long, then you're going to get sunburns. And these sunburns come because ultraviolet light can damage DNA. And in an attempt to fix it, they're going to be, the cells are going to be like really, really mad because the DNA is damaged. So that's why we get sunburned. And eventually, because the ultraviolet light is going to be changing DNA, you can get skin cancer, which is very, very fun. Generally, the higher you go, or the more you go up on the more energy means the higher chance you're going to get sick from whatever you're going to get hit by. So there's many ways to slow ultraviolet light, and like, so melanin is what makes your skin colored, and essentially melanin can block some of the ultraviolet light. However, ultraviolet is useful for producing vitamin D, which is pretty essential. So that's why you're going to see places with less sunlight, they're going to have lighter skins because they're going to have less melanin because they're going to need that sunlight to produce vitamin D. But places with more sunlight, they're going to have darker skins because they need to produce more melanin to block all the UV light so they don't get skin cancer and die. So the ozone layer also slows down ultraviolet light. And also sunscreen is a very good way to slow down ultraviolet light. So sunscreen prevents sunburns, right? You put on sunscreen during the summer, and you know this fact. And the ozone layer is like a section of air in the stratosphere or in the atmosphere. And it's going to prevent some of the UV from going through. So it mainly prevents UVC. So you have like these sections of UV light, can be classified into UVA, UVB, and UVC. And UVC is the highest wavelength, and it's going to be the most dangerous. And the ozone layer blocks a massive proportion of UVC, and UVB is like less dangerous than UVC. So it's not blocked as much, and a lot of UVA gets through, but it's okay because UVA isn't actually that dangerous. So, whoa, there's many ways to slow down ultraviolet light and the dangers that it causes, like skin cancer. And next, we're going to go through X-rays, and they're going to be shorter than UV and longer than gamma. Wow, it's almost like it's going in order. Okay. It can range from 0.01 to 10 nanometers, so this is already really small. 1 nanometer, I said, was 1 billionth of a meter, and we're already getting to like 0.01 nanometers, which is very cool. There's many sources for X-rays. So obviously the X-ray machines are going to produce X-rays because that's how they work. And they're also going to get X-rays from natural sources like radioactive decay. Not everything that is natural is safe. Obviously, radioactive particles are not very safe, and sometimes you can get X-rays from radioactive decay. So over here you can see like how these different types of radiation pass through things. So X-rays pass through a lot of things, but gamma rays ultimately will pass through the most. I'm going to explain gammas later. So one of the dangers of X-rays is that they give enough energy to like the atoms to like change the atoms or ionize the atoms. And if your atoms like start ionizing, that's going to mean that they're going to be super duper reactive and they're going to change, right? So obviously it's not very safe to have your atoms in your cells start ionizing, right? So X-rays can cause mutations and
But what happens if they change? Like, what do they change into?
I can explain what they change into, but this is not a chemistry class. But so, ions is what they change into. Ionization changes atoms into ions. Okay. So X-rays have a low chance of mutating cells, but over long periods of time, if you're exposed to X-rays for a long time, then you're going to raise the chance of getting mutations, right? Because even though it's a low chance, you're like going into that low chance a lot of times, and eventually you're just going to get cancer because of X-rays. So this is why whenever you like go to the doctor, you're in like the full blast of the X-ray while the doctor is hiding behind the wall. It's because you yourself have a very low chance of getting from getting cancer or sick from the X-ray, right? Because you're only getting hit by the X-ray once. But the doctors or the nurses around you have to deal with the X-ray like every day and have to like take X-rays of a whole bunch of patients. If they like got into contact with the X-ray that many times, they're eventually going to get cancer and you have mutations, right? So this is why you generally see doctors hide behind walls while you're like in the middle of the X-ray, right? So X-rays have many medical uses, right? If you've gotten your X-ray taken at a doctor, if you look to the right, there's a whole bunch of medical images from X-rays, and they can allow you to see like all of these little metal braces that are sometimes put into people. It can also be useful for diagnosing diseases because we can see what's going on inside the human body. And also, X-rays are useful for airport security because X-rays can go through most things, but then not go through metal, so then you can see who has the metal and if there's metal, right? So those are some of the uses for X-rays. Finally, we have gamma rays. So gamma rays, they have the smallest wavelength, so less than 0.001 nanometer. So an atom, if you the size of an atom is 0.1 nanometers. So gamma rays have a wavelength that is 1/100th the wavelength of an atom. So that wavelength is unbelievably small. And as such, they have the shortest wavelength. And because of that short wavelength, they have the highest energy. So there are many sources of gamma rays. So gamma rays are generally produced from space in a whole bunch of like different high energy space things like supernovas and neutron stars, right? These are high energy space things that create gamma rays. And actually, NASA likes taking pictures focusing on gamma rays because we can see where all of this sort of high energy activity is happening. So over here on the right, sort of a picture of space trying to see all the gamma rays, and we can see that a lot of things are happening in this intersection, right? So gamma rays can also be produced by nuclear reactions and lightning. So lightning actually produces gamma rays, but it's not going to be like that dangerous because it's not going to be very much. Generally, if you're getting a lot of gamma rays, it's going to be coming from nuclear reactions, which are not very good for your body. So the biggest dangerous thing about gamma rays is that they just go through everything because they have such high energies, right? So on this thing 2 slides ago, or 3 slides ago, the gamma rays can go through like cement, right? So obviously the gamma rays can go through a lot of things. And as it goes through the things, it damages everything that it passes through. It damages DNA, it causes cancer, all that kind of good stuff, and causes radiation sicknesses. And it essentially is what causes nuclear weapons to like just be terrible after you fire a nuclear weapon, and why it's so hard to live in a place after you explode a nuclear bomb. And actually, even though gamma rays causes cancer, right? Sometimes gamma rays can be used to treat cancer. So essentially, as you can see on this image on the right, you shoot a whole bunch of gamma rays because gamma rays can pass through a lot of things at one specific target, and you can destroy where the tumor is or what's causing the cancer, right? So destroying specific cells can allow you to destroy cancer or to treat cancer. And gamma rays, because they're so good at destroying everything, they're also very good at disinfecting stuff because they kill a whole bunch of microbes. So I was going to do a Kahoot, but right now it is 8:01, which means that we definitely won't have time for a Kahoot. But yeah, that was my class on lights and an introduction to the EM spectrum. Oh, all right. So does anybody have any questions that they would like to ask? Do you guys want to stay late to do the Kahoot?
Yes.
Okay then. So I guess we can do the Kahoot then.
Yes. No, sorry.
But if you need to leave, since this class is supposed to have ended 2 minutes ago, feel free to leave right now. Otherwise, we can do Kahoot. Oh. All right, no seeing the questions. All right, looks like we have 32 participants minus me and the Sage account. That's gonna be, 31. So looking for 29 people. Whoa, good for you. Somebody who's listening to music. Wow. Anyways, this is just gonna be on what we covered today, waves and sound and a whole bunch of stuff. Does anybody have any end of the year Kahoots at all?
We did English Kahoots for English class. We did like irregular verbs and everything.
Okay. All right. I'm going to wait a little bit, see if more people join. I don't think we're going to be able to get the full 29 people because it's probably some people who are just like, I don't know, they might be just AFK to their computer or something like that. So I think I'm going to start in like, I don't know, 40 seconds or so. Or if nobody joins in the next 20 seconds, I can start.
You have the same ad blocker than me.
What?
You have the same ad blocker than me.
Oh, I see. Looking at all of my tabs I see. That's fine. Whoa, it's been 40 seconds since I said that 40 seconds. So, we can start then. Yeah. The lag is probably pretty terrible.
Yeah, I know. I couldn't see anything.
Oh, oof.
Can you read the answers? Like,
Oh, what?
can you read the answers? Because sometimes your screen freezes.
Okay. I guess I can like read the questions and the answers if you guys want. Yes, definitely elemental master. Okay, no, it's electromagnetic. Whoa. All right. Wait. All of these things are covering. Okay. Oh my God. We need to find the next button. It's underneath all of the where I can see the Zoom participants. Whoa, person is in first. All EM waves travel at the speed of, or the red is sound, blue is light, yellow is dark, and square or green is relativity.
Light is supposed to be with yellow. No logic.
Rip logic. Yeah, all EM waves are travel at the speed of light because they're just light, right? Okay. Oh, person falling and Monkey Mon taking first place with Monkey following behind 2 points. Yes.
Monk.
All right, this question is radio waves have its multi-select. And red is the greatest frequency, blue is the longest wavelength, yellow is the shortest wavelength, and green is the smallest frequency.
Select everything.
No, maybe it's everything, but it probably isn't having the shortest and the longest wavelength, right? Whoa. Okay, so radio waves have the longest wavelength and the smallest frequency. Wow, 13. All right, Monkey continuing first place, but Monkey fall. It's third place. Okay,
Monk.
not confusing at all. This one is also multi-select. Why are radio waves so good at traveling long distances? Red is yes, I can definitely spell. They move through the atmosphere easily. blue is they travel more quickly than other EM waves. Yellow is they can go through a lot of building materials, and green is they can bend around corners and obstructions.
It's pretty obvious.
Everything.
Unfortunately, it's not everything, but yeah, they can easily move through the atmosphere. They can bend around corners and obstructions, and they can go through lots of building materials. But unfortunately, they do not travel more quickly than other EM waves, because all EM waves travel at the same speed, because they all travel at the speed of light. Whoa, there's somebody just dropped a lot, and Jessica is now first place at 5,536 points. Oh, all right. 5. Multi-select. Infrared is commonly called. And the option choices are sun rays is red, heat is blue, photon radiation is yellow, and thermal radiation is green.
Everything.
I say this is a multi-select. Well, only one answer is right. It was thermal radiation. Infrared is separate from heat, unfortunately. So we have those who said heat and thermal radiation. So see if the leaderboards change. Wow, not very many people got points, but Monkey Moon is got points and is now right behind Jessica. Whoa. True or
I'm
false?
too good. I'm last place.
There's a frequency associated with the color purple.
I understand everything.
Whoa, 6 people actually said true. Okay, there is no frequency associated with purple. Purple is what happens when we see both red and blue frequencies, and there's actually no frequency that is corresponding to purple, unfortunately. So clearly what you're seeing right now in front of your screen is totally not purple, but a combination of red and blue. I mean, that's what a whole bunch of the colors are, but just combinations of other colors. Okay, question 7 is a multi-select, and it says UV is useful for. It says red is tanning, blue is thermal imaging, yellow is disinfection, and green is preventing cancer. Yes, last place, goals.
Random.
Whoa, wait, oh no, I messed up, okay. It's definitely not good for thermal imaging, it's definitely tanning and disinfection, but I am stupid and I forgot to mess around with everything. Oops, and oops. Rip. Okay, so it's definitely supposed to be red and yellow. I'm very sorry for those of you who got it wrong because I was stupid and I forgot to switch it. But okay, so originally I generally what I do for Kahoots is I have random number generators decide where the answers go. Rip to people who fail a whole bunch of places because of me. Sorry. Okay, what can protect against UV radiation is a question. And red is serotonin, blue is melanin, yellow is sunbathing, and green is ozone. Okay, hopefully I didn't mess with these answer choices, and hopefully they're actually the right things instead of the wrong things like they were last time. Oh, melanin and ozone, they are the ones that prevent UV radiation. Very happy that nobody said serotonin. Okay. Oh, this is certainly very close heading into the last 2 questions. 400-point lead, but 400 points behind is second place, 400 points behind is third place. So let's see if somebody can catch up to Eli T. Oh, 9 is a multi-select and is also worth double points. Why are patients exposed directly to x-rays while nurses and doctors are not? So red is doctors and nurses have weaker protections against cancer. Blue is repeated exposure can cause cancer. Yellow is doctors are trying to give the patients cancer to get repeat customers. And the green is patients are better equipped to deal with the negative effects of x-rays. Sorry, was this a multi-select question? Only one was correct, and that was repeated exposure can cause cancer. Sadly, doctors are not trying to get patients to get cancer to get repeat customers. And that would be, yes, these are the, what is it, conspiracies in the doctoring or medical industry. Yes, more x-rays means more patients. All right, question 10 is a multi-select that is worth double points. Why are gamma rays dangerous? Red is they have enough energy to go through anything. Blue is they can change DNA. Yellow is they cause radiation sickness. And green is they cause mutations in cells. Correct answer was everything. So if you said everything, then that would be completely correct. But gamma rays are dangerous for all of these reasons. And fortunately, some people might have only looked at the first two and been like, yeah, it's definitely going to be only two. Or look at the first three and said, yeah, it's going to be only three. But it's all of these. And if you notice, this is worth double points. And since each of these are worth 1,000 points, this one question alone was worth 8,000 points. Yes, balanced. See how the leaderboards are shaken up by the last question. David A. 13,662. Eli T. Second place. First place with 15,990 points. Ever, who was, I don't think they were on the leaderboard, but nice job, everybody. Okay. So that is the official end of class. So feel free to leave.